Today, man looks out farther into the universe than ever before and hunts the tiniest subatomic particles using technologies barely envisioned even a few short years ago. Driven by the need to understand the world around us and how we fit in, we create the machines that allow us to continue exploration with the hope that someday we may unlock the answers to the really big questions.
The question that I think appeals to the average person, not just the specialist, is one of origins. We know that people haven't been here forever. We presumably evolved from some other more primitive life form, and that from something more primitive. But there also was a time before which there was no life at all, and before that, no planets. Where did it all come from? That's the fascinating question. Well, in some sense, the universe as we know it originated in the Big Bang, but that was a partial creation. It only made the lightest elements. There would be no planets like Earth and no life if it weren't for the action of the stars and the nuclear reactions there. So when we study the stars, we're studying our own history, we're studying ourselves.
If you would reduce it to the basics, the question that we're all interested in is, why are we here? How did we get here? What are we made of? That's not the way we phrase the question. We usually phrase it a tiny little bit about the drip line, or what is the full extent of the periodic table. But at the end of the day, we're trying to find our cosmic history. We're trying to connect ourselves to the quark soup that was there at the beginning.
But how far do we go, and at what cost? What are the implications of abandoning exploration in frontier science? And what are the rewards for moving forward in these fields? If the cost of science exploration is higher than ever, the stakes are also higher as we continue to examine the small matter of big science.
Well, if you go back several hundred years and you look at what nations valued, not all nations, just the nations that were wealthy enough to explore, they were interested in finding other lands, other resources, some acquired by trade, peaceful methods, others not so peaceful. But at the end of the day, what mattered was that a nation's understanding of its place in the larger world grew. And that is not something all nations have the luxury of partaking in. In modern times, of course, the entire world is mapped. So exploration is not so much, is there new land we've never seen before? Exploration now can be thought of as the search for ideas. When you're not actually advancing a space frontier, of course, the universe is large. Many shores await our discovery in the cosmos. But combine that with the fact that today, for me, the biggest frontier is the frontier of knowledge, the frontier of understanding how the universe works. And the nations that embark on these epic adventures of discovery are those who gain great economic wealth from those discoveries. They gain an important sense of security, and those are nations that get remembered throughout all of time.
As we look out over the next generation or two, I think it's pretty clear that frontier science is going to be absolutely a major factor in shaping the world. Our growing understanding of biological systems, of materials, our growing ability to analyze data, helped in part by the developments in basic particle and nuclear science. All of those are going to be very important in shaping our understanding of the world and how we can manage human affairs.
The game changers, the things that change the rules of the game, that take us from the industrial age to the information age, come from basic research. And my favorite example is quantum mechanics. I can only imagine if you had to go and justify why you were studying quantum mechanics in the 1920s, that it would be an absolute disaster. I believe that in the 1920s, quantum mechanics was more mysterious than string theory is today, and there was less of an appreciation. Yet today, I'll just throw a number out there, that 40% of our GDP derives from quantum mechanics. And why do I say that? We live in the information age, so where do we create information? With quantum devices. Where do we store it? With quantum devices. How do we transmit it? With quantum devices. How do we manipulate it? With quantum devices. The information age would simply not be possible without quantum mechanics. And so I call that a game changer because it took us from the industrial age to the information age. And what that next game changer is going to be, we don't have the slightest idea. But we know, based on history, that there will be a game changer, and it will come from basic research. And 50 years from now, 30 years from now, 100 years from now, people will say, thank goodness they invested in basic research, because otherwise we wouldn't be here where we are now.
There is what I would call a whole science and technology enterprise. It starts from the very basic discovery science, simply trying to find out about the natural world. It then extends to, well, how can we start to think about applying those phenomena to do things that are useful to us? And then the whole technology discussion of how can we then take that application and build it into useful systems. We need the whole continuum. If we stop discovering things, we will not have the technologies that we'll need in the next several decades.
We live in exciting times. Sometimes that's not so good, but for this purpose, it's great. Three things are coming together. Observations. We're coming to have some of the largest telescopes with the highest resolution and the greatest penetrating power that we've ever had. We can survey the heavens at all wavelengths. We can look across the universe. We can see stars of all masses and all ages and measure their composition with incredible precision. And at the same time, our ability to model, to simulate, to build replicas of stars and galaxies on computers has been increasing exponentially for decades, but now it's hit a threshold where we can, with almost complete realism, from first principles, simulate the life and death of a star. We can do the three-dimensional calculation with all of the hydrodynamics and nuclear reactions and everything folded in. So that's two pieces of the puzzle, but the third piece is the laboratory data, the information that binds us to reality, the cross-sections, the half-lives, the natures of all of the isotopes that make up all of the elements that give the energy generation for the stars, that provide the building blocks of nucleosynthesis. And so laboratory facilities for that purpose are also being constructed, and these three things are coming together so that the next decade is really going to be golden.
If we're not the ones who find the solutions to the problems that face humanity today, other developing and developed countries are, in fact, investing huge resources, intellectual and financial capital, to find these solutions. And out of those solutions come products and patents and this sort of thing. So we may benefit from their innovations because we'll be part of a society that's been saved by them, but we will not benefit economically from it.
In 2008, the U.S. Department of Energy announced its plans to invest in a new facility for rare isotope beams.
EFRIB is a joint project between the Department of Energy, Michigan State University, and built on a foundation that was laid at NSCL over many decades by the National Science Foundation. It is fundamentally a facility to produce beams of rare nuclei that may not be abundant in nature but might be stable, and also nuclei that might have short lifetimes and hence have to be manufactured immediately before they get accelerated. Using beams like that, together with the right targets and instrumentation, we can basically start to explore vast unexplored regions of the periodic chart. We don't know exactly what we're going to find when we go out exploring like this, but they could have implications not only for our understanding of the universe, our understanding of how the elements of which we're composed are made, but also perhaps important technological problems through their radiative decays, or through perhaps, if they live long enough, we could start to make materials out of them.
EFRIB will be the ultimate discovery machine. It will be the best facility to conduct rare isotope research, which means producing, discovering and studying new species of atomic nuclei which do exist in the cosmos but which don't exist on Earth, and opening them up to scientific inquiry. It will be more than a factor of 1,000, sometimes a factor of 10,000 more powerful than anything we have in the United States to conduct this research with.
With EFRIB being the most powerful rare isotope accelerator at a beam power of 400 kilowatts, we will be either able to do experiments in shorter time than any place else, or we will be able to do experiments that can't be done anyplace else, because in the end, no facility can dedicate a year's worth of beam time to one particular scientific question. The users are scientists who do experiments, and they make inquiries about nature, and they could be making inquiries about the structure of atomic nuclei. They can learn about how the elements are made in stars, or they can learn about fundamental symmetries in nature, or how rare isotopes can serve society. And at Michigan State, we are designing and establishing this facility to support the Nuclear Physics Directorate's mission in the Office of Science in the Department of Energy. And we will provide this facility in about a decade, and then users from all over the world will come and do their studies here.
Nuclear science is a vital global enterprise, and there are scientists all over the world who both collaborate with each other and to some extent compete with each other, such is the nature of science. If you look at the science that EFRIB will address, we are right now among the leaders, but certainly there are very strong efforts in Europe, particularly in Germany, and also in Japan. When we have EFRIB up and running, I think that will put us in a clear leadership position for this science. That means not only will we have a first look at the knowledge, if you like, but we'll be able to attract quality researchers from around the globe to be working in the US on these problems.
The great idea of EFRIB being a user facility is that it is open for the best scientific ideas. So we're creating an infrastructure for discovery, and then we're inviting the best minds in the world to come to our place, think about what they want to do, and we'll have a process which filters out the best ideas from the not so good ideas. We make sure that the most brilliant scientists with the most brilliant ideas can conduct their research in a successful fashion. Science machines like EFRIB cannot be built just for one or two people. They're built for a community of scientists who are always in some friendly competition trying to push the envelope further out. So the scientific idea of creating a hub where the best minds of the world are coming together and having a facility whose mission is to make other people successful, that I think is the most powerful way to conduct science, to push the envelope further out. And in fact, actually, it is the best way to guarantee the optimum return on investment on the federal tax dollars.
By EFRIB being located on the campus of MSU, where we also educate undergraduate and graduate students, you bring together world-class researchers, people who are aspiring to be world-class researchers. They're looking for role models, people who have ideas. And this free exchange of ideas, together with the availability of a world-class research facility, is kind of a fertile ground to develop new ideas. And so it's important to have a hub, to have a physical location where people come together, exchange ideas, and develop new ideas.
There's several reasons why we need these new facilities, as expensive as they may be, and they are expensive. Because the further you advance the frontiers of science, the harder it is to make steps and go still further. And so it takes bigger teams and it takes bigger facilities. And so a lot of science is big science these days. But the payoff is also big. The problems we're trying to understand are very fundamental. You know, what is the nature of matter? What is the nature of the universe? Where did it come from? Where did we come from? How is it all going to evolve? And these questions, of course, interest scientists. But the thing that's sometimes missed is that there's often a huge spin-off for technology as well. You know, understanding nuclear physics better benefits technology in many ways. There's nuclear medicine, there's nuclear chemistry, there's reactor safety, there's nuclear safety. Probably 100 other things that have nuclear as an adjective that benefit by understanding nuclear physics better.
The search for origins has taken us places we might never have expected, from deep space to close to home. One such place is the field of medicine. The implications of isotope research and accelerated beams were evident early at Berkeley, where the first links to cancer treatment with nuclear science were established.
Lawrence came from South Dakota, Canton, South Dakota. He grew up there and then went off, was educated out of the state, went to Yale, and then came to Berkeley. And they were obviously an energetic family because he had a brother, John Lawrence, who went to Harvard Medical School, became a physician. And Lawrence was out here on the West Coast developing these cyclotrons, and he was always interested in applications. I mean, he wasn't an ivory tower physicist at all. He wanted, he'd got this great device, and remember, he won the Nobel Prize for the device, not for the discoveries it made. And he wanted to do everything he could think of with it, and he thought there must be opportunities in medical research. And he thought, well, who better to talk to about this than his brother, who he knew well, and his brother moved out to Berkeley and founded the Crocker Lab on campus. They were both studying uses of isotopes for treatment, but radioactive isotopes, but also using beams for therapy, neutron beams. In fact, I believe that one of the first people that they treated was their mother, who had an inoperable cancer that was treated with neutrons at the cyclotron.
Today, nearly 20 million nuclear medicine procedures are carried out each year in the United States alone to diagnose and treat cancers, cardiovascular disease, and certain neurological disorders. Many of the advancements in nuclear medicine have been the result of research investments made during the past 50 years, where these procedures are now a routine part of clinical care. Although nuclear medicine plays an important role in biomedical research and disease management, its promise is only beginning to be explored. In the western suburbs of Chicago, ProCure is completing the construction of its second proton therapy center, utilizing techniques and accelerator technology developed in nuclear physics.
Well, proton therapy is taking protons and using them to treat cancer. The benefit of protons is they're big, heavy charged particles. So it's like taking a bowling ball and rolling it down the alley and depositing all that energy into the cancer cells, knocking electrons out all over the place. And that's what it's doing, it's kind of creating thousands of ionization events.
Beauty of protons is that because they have that charge, they get attracted by the other molecules in the body. They go a certain distance and stop and give off all their energy. And we can basically dial up or down the energy depending on how deep we want to treat. It's a big advance over standard treatment, primarily because of what it spares, the tissues it doesn't hit.
The way I usually describe external beam radiation, the standard conformal radiation, is I liken it to a spotlight on a performer. You have many spotlights coming in from different directions, and where all the spotlights come together is this very bright white circle. But all around that spotlight is a lot of light that's being projected from that region. So when you think about it in the case of a patient, you're going to bring in many radiation beams from many different directions. In order to shape that beam to the target region, you have to come in from all those directions, and where all those beams come in from is going to be radiation dose, and where all those beams exit will also have significant radiation dose.
X-rays enter the patient and deliver their dose in an exponential pattern. They deposit energy at the beginning of the path, the end of the path, and all the way through the exit of the patient. The one huge benefit of protons is that the protons go in and they actually stop. So we can sculpt the dose around the tumor better. When we do that, we miss all the critical structures, which are always nearby tumors.
There are a number of advantages with proton therapy. During treatment, less of the normal tissue is treated, so there are fewer side effects. After treatment's over, less of the patient's body has been treated, so there are fewer long-term side effects. And because fewer cells have been hit by any kind of radiation, there's less of a risk of getting another cancer. And we worry about possibility that treatment could cause a second cancer, with proton therapy, we know that that risk is a lot lower. So basically, it spares during treatment, after treatment, in the long run.
This treatment is probably the pinnacle of what we can provide for the pediatric and young adult patient, because they have a much longer lifespan. If you damage the DNA of, say, a mature adult, they have the ability in their system, in their cells, to repair that damage. And that's the main focus of tissues that are mature. When tissues are still developing, they're spending a lot of their time growing and developing, and when you mutate the DNA, their blueprint for growth and development, you then can cause problems with tumor suppression or growth factors such that they could become aberrant and subsequently develop a second cancer in the future, which is one of the biggest concerns we have whenever we deliver cancer treatments to a young adult or to children.
I think that when cyclotrons were first developed, the least thing they had in mind was that we could use this to fight cancer. Where the big benefit comes is when pioneering scientists and physicians look at this and say, hey, this is a neat property. We can use this in other things too. One thing is killing cancer and being accurate and effective with it.
I think many scientists more or less abandon traditional disciplinary lines and see science as a continuum. In part, it's because we understand atoms and molecules pretty well. In part, it's because the instrumentation that we're developing really drives us to stretch across the scientific boundaries. And so you have biophysics, geobiology, nuclear geochronology, all of these sciences at kind of the interfaces are some of the most exciting things that are going on.
About 15 years ago, NASA started funding research programs that were cross-disciplinary, fundamentally cross-disciplinary. One of them was the Origins program. The origins of the solar system, of life, the Earth, of the universe. And when you do that, what you find is that you need more than your profession to solve that problem. The origin of life, for example, it's not just the biologist. You need the geologist to understand the conditions of Earth. You need the astrophysicist to understand where all these elements came from and how you got a solar system in the first place. You need the chemist to understand how do you go from inanimate molecules to animate life. Life is, by most measures, the most complex form of chemistry we know. So we've entered an era where the cross-pollination, not simply the collaboration of different disciplines, the cross-pollination of different disciplines is the way discovery is unfolding today.
If the world we live in today is driven by science, the drivers are the scientists. Without new generations of researchers, countries who lead the world today in innovation will cede their dominance and become second-class nations as others surpass them. Facilities like EFRIB may be part of the answer to filling the pipeline with new talent.
I think the most important payoff is sometimes overlooked is the training of the next generation. Without new data coming in, without facilities to work at, without experiments to do, we don't have new students. And in particular in the area of nuclear physics, the United States is terribly underdeveloped right now. Compared to where we were 30, 40 years ago, we're in dismal shape. We graduate in this nation of order 80 new PhDs per year in nuclear physics. And that's for everything that nuclear physics has to cover. Nuclear chemistry, reactors, new sources of energy. Who knows who will design the next breeder reactor that will put out less radioactive waste and be more efficient energy generator? Who knows who will find the next new radiotherapy for cancer? 80 people a year is too small a workforce to deal with this. And without these experimental facilities, the next generation is not excited, they don't come along, they don't exist, and the field dies.
When you think about the edges that we might have in the next several decades, there are some that are cultural, the rule of law, the ability to have intellectual property. There are some that are economic. One is, of course, people. We need to entrain a greater fraction of young people in science and engineering, starting from the kids in elementary school who wonder about what's going on in the heavens or in the world around them that they can see, through the students in high school and then on through the universities and so on. One way we do that is to just educate people about the wonder of the science. But another is to build the big machines, the big pieces of hardware that let us study nature better than we can. There's a tremendous attraction, a romance about them, big accelerators, big telescopes, big computers, and certainly facilities like that, and facilities like EFRIB, will help attract people into that pipeline, and of course give them the opportunity to contribute once they're in the pipeline.
Most people would tell you we need better teachers, we need more funding for science programs in school, this is what people will typically tell you. And I think there's a limit to how successful that can be. Because at the end of the day, your science class is just one out of the multiple classes you're taking in a semester. And no matter how brilliant your teacher is, they might even ignite a flame within you, sparking your interest in science. That teacher goes away one semester later. You move on to some other teacher. Not all teachers will be equal in this ability to inspire. Not only that, and most importantly, from where I see it, if there is no place for them to land at the other end of that educational pipeline, there is no incentive for them to want to become scientists. Doesn't matter how interesting the science. What that would do is it would raise the science literacy of the nation a few notches, because kids would know a little more science, might be a little more interested in reading about it. But to become a scientist, to want to apply scientific, technological, mathematical creativity to the nation needs a place for them to land.
I think there are lots of kids who are interested in science. You have to give them good science teachers, but then the most important thing is you have to give them a path into the future. They go into training, they go into graduate school, and they need to see what's after that. You can't just put them out on the street. For example, when the big science explosion and the post-Sputnik shock in the United States was happening, we built up sciences phenomenally in the United States. A lot of people got trained, and all of a sudden science funding dried up. And highly trained physicists and engineers learned how to drive taxis just in order to survive. That turned a lot of people away from sciences. The rewards don't have to be huge for a scientist. The rewards are in the discovery. But you have to give them, with a steady hand, a guarantee that they can continue on the path in which they have invested, often for more than a decade, that they can apply that knowledge in a fruitful way. So steady science funding with a long-term vision and with a good stewardship, I think, is a very important issue to maintain the scientific and technological supremacy of the nation.
The question, and I think a lot of people struggle with this, do we have enough people going into the science and technology careers? And I'm not sure we know the answer. I think the science literacy of the public, we know the answer. We need to do a better job there. You can't have a society that's run on quantum mechanics where people take pride in the fact that they don't know what quantum mechanics is.
I think it is very important to have a scientifically literate population. A lot of the questions which mankind is facing, global warming, having enough clean energy, all these important questions will not come from ideology. They will come from a lot of detailed scientific work and innovation. So if one wants to address these questions, it is good to have a population which understands what these questions really are about.
If we're to sustain the activity and progress in science and technology that we need, both to increase our understanding, but also meet some of the challenges of the next several decades, we need to maintain a vibrant science activity in this country. Given that most of that science is supported by the federal government, obviously the support of the people is essential. And for that to happen, people have to understand the role that science plays in society. I think there can and should be a greater understanding of that. After all, these are major investments of public monies. They need to be sustained over many years. And the more that we can get people to understand about science, the better we will be able to do that.
It is the role of the government to fund basic research, partly because no one else there's no incentive for anyone else to do it. And so I think it is important that the government fund the basic research. And the long-term health of the country depends upon it. So I think it also falls within the government's purview. If you do accept that, then the next question is, so at what level? And if you ask someone like me, if you ask a scientist, the level is higher. And so the hard question is, what is the proper investment? How much do you put there for today's problems, and how much do you put in the seed corn? And it's a hard question because, again, I think young people get really excited about basic research. And it's the young people, it's the next generation of scientists who are going to solve our climate and energy problems. And so the gateway to that is basic research.
So it's a tough decision for a nation. Do you maintain this onward march to the frontier and beyond? Or do you say, ah, too costly, let's just forget it, worry about something else? Well, I don't think Queen Isabella said, oh, this Columbus voyage, that's cheap, let's just do it. No, they gave a lot of thought behind the cost and the investment that she and Ferdinand made in Columbus's voyages. And Columbus was not the only explorer who they funded. They funded many Italian explorers. While Italy was busy building cathedrals, deciding that they can't afford or shouldn't afford or was not worth paying for explorers, Spain took on this mantle. And it's not an accident that today most residents of the Western Hemisphere speak Spanish and not Italian. It's just one of those consequences of how this plays out in the unfolding of history. Where do you invest your monies, and how much do you value discovery?
Modern science is a complicated interwoven net of different factoids which you have to put together. It's high risk, it's long term, the immediate benefits on the balance sheet of a country are not immediately obvious. Sometimes you have to pursue a line of research for many years. Some of the lines of research are not leading to anything, you can't predict this. Other lines require enormous investments to carry out, and those investments with long-term visions and high risk in that sense are typically not undertaken by companies which have to look at their quarterly balance sheets. So the only viable good steward of large-scale science, which is sort of driving the frontier of our current knowledge, is the federal government, which has enormous resources.
Science and exploration have shaped our world. It has changed us from builders of monuments to builders of great cities and societies. Where we once stood and looked in wonder at the heavens, we now see beyond them to the edge of the universe. Where we once questioned the ground we stand on, we now look into its tiniest particles. Our endeavors have taken us from the rifts of Africa to the modern world we know today, to the farthest reaches of the universe. As we begin the new millennium, we understand the drivers of our prosperity. But are we doing enough?
You know, when I think about the U.S. position in the rest of the world, I think about the number 6. That's how many times greater the U.S. prosperity is per person than it is in the rest of the world. We have enjoyed a tremendous benefit from that prosperity, but as we look forward over the next several decades, we can see many forces that will change the historical trend. One of the best ways that we can try to manage that situation is to have the world's best science and technology, and we need to take steps to make sure that that continues.
One of my favorite cartoons I saw was a kid talking to his grandfather. Kid is maybe late teens, and said, "Grandpa, you had nothing. We've got cell phones, and I got my iPod and GPS, and you got nothing, Grandpa. How did you even survive?" And Grandpa says, "Son, you're right. We didn't have any of that. That's true. What we were busy doing was inventing it." Now, what are you inventing for the next generation? The answer to that is nothing. All right, so we've been coasting on the investments of a previous generation, thinking that we don't need to keep investing. And you can coast for a while, and it looks like you're doing okay, but the seed corn has been eaten. And so as other nations begin to pass us by, and as no new discoveries show up, that's when you're just headed for the cliff. So I'd like to believe that as a nation, somebody will wake up. If not the politicians, then the heads, captains of industry. They'll wake up and say, look, we're as a nation growing rapidly poor. What's the source of that? It's because we're not investing in our science and technology, which we've known since the Industrial Revolution is the engine of economic prosperity. So it's time to reinvest in ourselves, to reignite the flame of creativity so that we don't move back into the cave as we watch the rest of the world carry forth the torch of cosmic discovery.
For the United States to maintain its position as an international economic force, it must invest in science and technology. The Facility for Rare Isotope Beams at Michigan State University is a prime example of the type of infrastructure necessary for America to continue being a powerhouse in the global economy. Only a sustained effort by the private and the public sector to commit to research and education will allow America to compete for quality jobs of the future.